Okay, welcome back. And before we go on into regression, I wanted to talk more about the correlation coefficient and the test for significance, and what the underlying assumptions are when we go on. So the idea is this. We want to see if there is a significant relationship between two variables. So we look at the scatter plot and we see if there's a pattern. And if there's no discernible pattern, we don't go on. But if there is a pattern, then we can correlate, that would be reason to correlate the quantity, right, the correlation coefficient. And then what we want to do is we want to test, right, that's what we're doing with the hypothesis testing, is testing to see whether that correlation is significant. And if it is significant, then we want to go on to the regression analysis and get a regression equation. Why? Because what is the correlation coefficient measuring? It's measuring the linear relationship between two variables. And if that relationship is significant, then we're going to want to know what the nature of that relationship is, and that's where the regression comes in. So here are the assumptions that we're making, and these are assumptions that we can test as well, but these are the assumptions that we're making because we don't know what the actual relationship is. We're going to make some assumptions about that relationship as we go on, and these are assumptions that may be true or not that we can test. Okay, so in a population, if we were to take, and if there was a linear relationship, we don't know what that equation is. What is the equation that actually measures the true relationship? Okay. So we might look at that as y, because if we're talking about the true relationship, then this would be a perfect prediction. It would predict every value of y. So y is equal to what? Beta 0 plus beta 1 x, right? Where we use these Greek letters for the actual values, right? These are the parameters, right? The parameters of the regression equation. But we don't know what those are. So what do we normally do? Well, we replace these with our estimates. What are the best estimates? The sample, it's from the sample, right? So our best estimates that we're going to use is going to be y hat is equal to what? Well, b0 plus b1 times x, or for our purposes, we just replace that with a plus b x. So we're going to use our sample to try to estimate, right, the target, the true regression, the true relationship. So in order to do that, we're going to make some assumptions, right? So the first assumption that we make is this. One, there is a linear relationship in the population that models the average value of y for varying values of x. Well, what does that mean? It means the expected value of y for each particular x value lies on a straight line in the population. So in other words, we can take the average for each value of y. So we're talking about y bar, right? So for a particular value of x, then we're going to have a y bar value. So if we have x1, we'll say y bar 1. Okay? x2, y bar 2. Okay? Which means if we take, for a particular x value, we take all of the possible y values that we could get, okay? We take the average of those. These values should lie in a straight line. That's the assumption, that the average value of y for the values of x, okay, should lie in a straight line. So as x changes, the average value, the expected value of y should lie in a straight line. That's the first assumption, okay? 2, the y values for any particular fixed x value. Okay, so that's going to be important. Okay, so let's say we have a fixed x value. Okay? So we have a fixed x value. For any particular fixed x value, the y values are going to be normally distributed about that line, about the line. Well, which line? The line that we talked about in the first assumption, right? So the line of means, right? So if we take a particular x value, then we're saying that the y values, for all the y values for this particular x value. Well, what do I mean by all y values? Well, remember, this is based on a sample, right? So again, if we take another sample, for that value of x, we might get a different value of y. And if we take another sample, and we look up this particular fixed value of x, and we see that y value, it's going to be a different y value. And we keep doing the sampling, right? So this is all based on sampling. So the more samples I take of the same size, and I look up this value of x, and I say, okay, what's the corresponding value of y? Then I'm going to get a bunch of values of y for this fixed value of x. Well, the assumption is that all of these values of y, okay, are going to be normally distributed. So if we have a value of x and we take all of these values of y based on our sampling, we're going to say that the values of y are going to be normally distributed. So y is going to be normally distributed. About what? About y bar. Okay? The average. Okay? So for every fixed value of x, we're going to say that the distribution of y is going to be normal with about y bar. Okay, so that's the other assumption. So now, assumption one, here's where assumption one comes in. Assumption one states that these normal distributions are centered on the line. So for a fixed x value, the mean of the normal distribution of the corresponding y values is the y value predicted by the regression equation, which is going to be x bar. Okay? Now, okay, so now the next thing is, the next assumption is that the standard deviations, okay, again, this is for a particular fixed value of x. The standard deviations of the y values is the same. Oh, yeah, will be the same. Okay? Regardless of the value of x. Okay? So, again, so here's the thing. First, the fixed value of x, okay, for a fixed value of x, the y's are going to be normally distributed about the mean y bar, and it's going to have a standard deviation, sigma. Sigma of the y's okay, so the standard deviations of the normal distributions described in the last assumption regarding the normal distribution of the y's are all equal. Meaning, that regardless of the x value, so if we could change the x value, now the y bar may, the y bar will change, right, depending on the x value, but what's not going to change is sigma. The standard deviation of the y's will be the same regardless of what the x value is. Okay? So this won't change for any particular x value. Now, also, the other thing too is the residuals. Now remember, we didn't talk about residuals yet, but residuals are the difference between the observed value and the predicted value. Okay? So a residual is the difference between the predicted value, or excuse me, the observed value minus the predicted value. Well, what's the predicted value? Well, the predicted value is just y hat. It's based on the regression equation. Okay? So your regression equation, y hat equals a plus bx. Well, the observed value is just your y, right? That's just going to be y. That's the observed value in your y data. Okay, that's just what it is. Minus the predicted value, which is y hat. Okay? This is what we call a residual. Okay? So now, the difference between the observed values and y. What we're going to say is that if you plotted all the residuals, so you measured all the residuals from the data, okay? There should be no pattern to the data. So if we do what's called a residual plot, where it's just a plot of the residuals, and the residuals, it's going to be anywhere from 0 to, well, it's going to be centered around 0. Okay? So if you look at a residual plot, you shouldn't see any kind of discernible patterns. Nothing trending up, nothing trending down, nothing fanning out, fanning in. No certain patterns. Okay? So if there's no pattern to it, if it just looks like just going straight across like a cloud of dots with no discernible pattern, then we're going to say that the errors are mutually independent. Okay, so that's what we are going to assume, that the errors are independent of each other. Okay. 5, the data are produced from a well-designed random sample or randomized experiment. That's a given. Okay, that's the other thing too, is we're assuming that the data that this is coming from is from a completely randomized design or study. Okay. Or excuse me, experiment. So again, the data are produced from a well-designed random sample or randomized experiment. Okay. So now, assumption 2 and 3, the one that I talked about regarding the means being on a straight line and the distribution of y being normal for a fixed particular value of x, those are called the normality assumptions. Okay. And those are the things that we can test. And the constant variance assumption, as far as the sigma. So for assumptions 2 and 3. So the second assumption, where we're talking about the distribution of y for a particular value of x, that's the normality assumption. The third assumption, where we're talking about the distribution, for every value of x, the standard deviation of the distribution of y's will be the same for all values of x. Okay, that's the constant variance assumption, or what we call yeah, this is hard to say. It's a big word. Homoscedasticity. That's what it's called. Okay. In other words, constant variance. Homoscedasticity is what it's technically called. Other than that, that's about it. So next time, we're going to start on regression analysis and how we get a regression equation to model our data. And then we'll talk more about that. But I wanted to make sure you guys understand the assumptions for doing the correlation coefficients, because these are the assumptions that need to be met going forward with the regression analysis. Okay, see you next time. Have a good day.